Well, good day, ladies and gentlemen. I'm Rick Moore. I'm a retired Lieutenant General from the Air Force, and we are here today to talk about data security. I currently serve as a strategic advisor to Entrokey Labs, and Entrokey has some solutions that we think are revolutionary in the world of data security. This is a pressing problem now. Why and what has changed? Artificial intelligence now has the ability to see patterns in random numbers that allow adversaries to take advantage of vulnerabilities in low entropy, low randomness in encryption keys. That threat is here and present today. On the future scope, in the very near future, comes quantum computing. And quantum computing makes all of the encryption that we have today at risk of becoming irrelevant. And depending on what you believe about when quantum computing comes, you either believe that this threat is on our doorstep, or you have to believe that harvest now and decrypt later comes fairly quickly. In any case, the data security risks that we face now, they're here. This is not a tomorrow problem. This is a today problem. So what to do? There are a couple of ways to approach this. One is to do nothing and just hope that this threat doesn't become real. Obviously, those of us that are involved in this business think that that's a very risky strategy, and it puts at risk not only our companies, but also our people, and even it could potentially place our national economies at risk. If we're going to implement a solution, we could implement a hardware-based solution, and we'll talk through what some of the vulnerabilities of that are in a little bit. We could implement a hybrid solution, a combination of hardware and software. Those solutions still have the same vulnerabilities that pure hardware solutions have. And then finally, we could implement a pure software, a software-only solution that could work in any environment under any conditions. That hasn't been possible until now, but Entrokey offers a way to implement a pure software-only solution. So we're going to talk through this today, and we're excited to spend a few minutes with you and give you our perspectives. I'm joined today by David Harding. David has 30 years of experience in the C-suite. He now serves Entrokey as its CEO. He has multiple patents in everything from biometrics to digital ID to scalable computing, as well as cybersecurity, certainly an expert in this field. I'm also joined by Professor Scott Streit. Scott is a recently retired research lead at Villanova, has also served over 35 years as a trusted government agent as well as a C-suite executive. And Scott brought in the foundational patent for Entrokey Labs, and it was his 46th. His experience in the realm of cybersecurity, identity management is certainly puts him at the absolute top of this field. So with that, we'll start off with David Harding. David will give us an introduction about Entropy and why Entropy is the foundation of information security.
Thank you, Rick. Yeah, Entropy is the foundation for encryption. You made some very good points about where we stand with encryption today. Encryption has been the safety net. It's been the way that we protect our personal information, our banking information, the way that governments protect their state secrets, and all of it is at risk for the very reasons you described, both AI and the future of quantum computing. So what's the problem? Well, the problem is that the encryption is resulting in low quality encryption today, the algorithms we use, and the algorithms we're starting to migrate to for post-quantum use. We're very glad to see that transition to post-quantum algorithms, but at the end of the day, it's the key, the encryption key, that's going to either allow that algorithm, that encryption algorithm, to create a truly AI and quantum resistant output or not. And that key, the element that's so necessary inside that encryption key, is entropy. And in this case, entropy means chaos, complete and total randomness. Entropy is not exactly easy to create, but I will tell you that the keys that we're using today do not contain the level of entropy to be able to create quantum resistant output, regardless of the algorithm you use, whether it's today's algorithms or tomorrow's post-quantum algorithms that NIST is approving. This isn't David Harding saying that. It's not Scott Streit saying that. It's NIST saying that even if you have a post-quantum algorithm, Kyber's Crystal, or whatever one you want to use, if you do not have a key that has a high enough level, a high quality level of randomness and entropy, you're still not going to get a safe output.
So I want to come back to this concept of not enough entropy, but before we do that, I'll turn it over to Professor Strite and get his thoughts on why entropy is so difficult to produce.
This is a very interesting topic. I started playing around with generative AI because I wanted to do something personal. And so frequently in our careers, we jump into something personal and lo and behold, someone named Dave Harding says, hey, look at this problem. And it aligns with something you've been playing with. And just such a thing happened here. I was playing around with generative AI because I was wondering if I gave generative AI all of Cole Porter's compositions, would it write me a song like Cole Porter? So in order to do that, that's a generative AI problem. And I started working on that and playing with that. Contemporaneous to this, my good friend Dave Harding calls me and says, look, we're looking at entropy. We have these devices. I start to dig in a little further at the devices, and I started to say to myself, how is this any different than composing a Cole Porter tune? They're both generative AI. And that's the exact approach we took with this. We basically took all of the cosmic data, about 40% of it is bad, throw it away. Because inside of an attempt to do randomness will be some patterns. We throw those away. The other 60% we train on. What does that do for us? That gets us very, very high random data. Now, what's the challenges to this? The challenges to this are the techniques that are available to us today are statistical. But what do we really need? We don't need statistical. Anybody can sit with a calculator and come up with randomness statistics. What we really need is real smarts to say, hey, there's a pattern in here, not a pattern that Rick can see, not a pattern that Dave can see, but a pattern the computer can see. So we put two pieces of a problem together, a different way to measure entropy, which looks for patterns and not just statistics, and merges it with AI, and then uses those same techniques to generate very high entropy AI.
So, Scott, you talked about measuring entropy, and David mentioned the concept of not enough entropy in current keys. Can you give us an idea of what it is that we use to measure the level of entropy in the keys we produce? And is this sufficient to do that?
So what we have right now to do it, and I know Dave would agree with me on this, is not sufficient. It's kind of throwing your finger up in the air. Now, it's not all bad news. Because when I looked at how NIST was doing this, I called Dave and said, Dave, I hope I can get a neural network to converge. This is pretty sloppy. But we got some normalcy in it. We got some class boundaries, and we have real generative AI that works reliably. No question about it. We also have future techniques at Entrokey that are going to allow us to search for these patterns. They're already in and working. We just need the spec committees to adopt to them. That will give a score based upon the probability of any pattern being inside the key. So now we can do statistical AI, pattern matching, and give it a score between 0 and 1. When the market grabs onto this as a better indicator of entropy, we can now train our network with this and really the sky's the limit of how far we can go with entropy. And we have some papers that are out there on this. And what's real interesting is the intersection between key length and entropy. And we're working on that type of paper right now. So we're not just looking at Entrokey as here's your problem, here's how we can solve it, but here's the problems that are coming over the next 4 or 5 years. And we're already working on engineering those.
Yeah, I like the thought that there's actually a way to measure this, and there actually is a way to produce a score, and that we actually probably need to transcend NIST before we're going to get to something that will allow us to handle the post-quantum instantiations of encryption. Fundamentally, at the end of all of this, however, what we're talking about is information security. And as I mentioned, there are dramatic risks associated with current levels of protection for our data. We're putting our companies, we're putting our future, we're putting our people, and we're putting our economies at risk. But it doesn't have to be that way. That's not a guaranteed future, and it isn't inevitable. So back to you, David, to talk about Entrokey's solution.
Well, as I said earlier, we believe that high quality entropy is the foundation for encryption. In fact, we don't just believe it, we know it. The industry knows it. So when Scott and I started working on this problem and he started addressing it with AI, the first thing we did was came up with a working model using AI. We started with cosmic radiation, capturing cosmic radiation and the byproducts of cosmic radiation, which gave us our training data. As Scott said, about 40% of it wasn't really usable because it didn't have a high enough level entropy. And at the time, we were using NIST scoring test harnesses to look at that data. We were able to capture low 60% amount of good entropic data. Then we were able to condition it. And then we were able to train the model that Scott has put together. And most importantly, before we ever talked about it, we issued we put in an application for a patent around this. I'm very proud to say that it was awarded. Not only was the patent awarded, it was awarded in less than 90 days. Both Scott and I hold multiple patents. I will speak for both of us in saying that it usually takes a few years to get a patent awarded. This took less than 1 business quarter. The reason we went to an AI model to do this is because every other model that tries to do this is hardware based. You've probably heard of quantum random number generators. And they suffer from the same problems we ran into in using cosmic radiation, because we were basically using a cosmic radiation to power a quantum random number generator. And that's how we got our initial data. The problem with QRNGs is multiple. First of all, they're fragile. You can't put it on the back of a Humvee, for example, in a mobile data center. It's not going to work. You certainly can't put it on an F-35. It's going to break. So how you deliver that or where you use that QRNG becomes very important. The other problem that exists is they're susceptible to ambient interference. And ambient interference can affect the output and actually degrade the output. Elevation, temperature, vibration, these are all ambient interference types that will affect a QRNG and degrade the entropy levels that you get. We didn't run into this problem with the AI model that Scott created. In fact, we got to the point and are now at the point where we're generating pure entropy. Through the NIST, just the statistical testing, we're scoring 0.99 plus out of 1 being perfect entropy.
And check this out, Dave. This is what's really exciting about it. We're getting to that level of statistical tests, but the NIST test can't find patterns.
Exactly.
We'll be able to hold on to the statistical and find patterns and give a score. If you get pure randomness, inside randomness can be a pattern. Okay, that's what's there. We're able to detect all patterns and assign a score to it. When we do that, right now we're at this incredible high level with respect to the NIST standards. What happens when we get to an incredible high level with pattern recognition? Now you start to talk about measurements that are off the charts. And that's where we're going. That's where we're going every day.
That's exactly right. In fact, we already have our first product out that does this, and Scott is continuing to improve upon it. So when you look at the NIST test harnesses, both Scott and I have gone through that code. It is open source, and we've actually learned quite a bit from their model and how they score it using standard statistical models. And you can get an entropy score and get NIST certified. But to Scott's point, that's only half the story. So we're creating this great random and entropic data stream, and we're doing it at scale, by the way. We generate megabits of data, truly random and entropic data that we can verify statistically and also through AI to find hidden patterns. But we can do that in milliseconds. Just a few days ago, a quantum computer company came out and was very excited about creating less than 100,000 bits of random entropic data and testing it. It took 18 hours. We do that in milliseconds, and we can do it anywhere. It is a software-only solution that can run on a server, a desktop, a laptop, even a mobile device, at the edge, anywhere, and generate massive amounts of entropic data for the generation of encryption keys. And most importantly, we can score it. And as Scott said, it's not just about, say, a megabit of data. It's actually being able to score the encryption key itself. And that is unique.
It's interesting, Dave. When we came up with the idea of scoring and how we were going to do this, We always assumed that it was going to be fixed length keys because NIST has fixed length keys, but ours work for any size. You give it 2 bits, it's going to give you a number. You give it 2 million bits, it's going to give you a number. And it answers the question that most of us in this field have been unable to answer. If I get a chunk of 1 million of randomness, what can we say about each of the components? NIST tells us nothing. We tell you everything. We can take any size of it and give you the entropic score for any subcomponent of it.
And I'm going to come back to the following statement. We don't have limitations. We don't have hardware fragility. We don't have ambient interference issues. We can literally run anywhere and generate millions, tens of millions, hundreds of millions of highly entropic, verifiably highly entropic encryption keys across the entire spectrum of encryption key types, whether that be modern day algorithms today, like elliptical curve algorithms, or even the newer PQC algorithms that NIST is certifying today. We build keys for any of those algorithms, and they're highly entropic. They are verified. The veracity of those keys is verified. And we can do it at scale.
Yeah, so all that is great, but there are a couple other things that I'd like to explore. David, you've been a CTO for multiple companies, including publicly traded companies. There are a couple of facets that I think would be interesting to discuss just a little bit. One of them is cost, and one of them is hardware versus software in terms of upgrades to the network and downtime, fragility. What do you have?
Well, as you pointed out, I've been the CTO of several companies, including public companies. I will tell you my biggest fear when I was CTO of a public company, going to my CEO, going to my board, going to Wall Street and saying, well, guys, we have to upgrade, and this is a rip and replace. I have to remove something that is working. We have a whole lot of knowledge on how to support. That our cost of ownership isn't going up year on year. We've crossed that fulcrum, and now it's going down. And we know what the vulnerabilities are, and we know how to deal with that. But we're going to replace it with something brand new, have no experience. Cost of ownership is going to go up year on year for a minimum of 5 years. And I really don't know what all the threat vectors are yet. You can imagine, one, the unease on my part, and two, the unease by my boss, the board, and Wall Street. That's a non-starter. In this industry right now, that is exactly what people who are trying to solve this problem are telling companies that and governments that they need to do. That doesn't work. We've taken a completely different approach. Instead of asking for a rip and replace what you're using, companies are already having to address moving to new algorithms. As the company that can generate the high quality quantum and AI resistant encryption keys, we work with their existing systems. For example, we've integrated in things like OpenSSL, Boring SSL, Keycloak, all the standard tools, HSMs, all the standard tools that people are already using. So they don't have to yank anything out. They don't have to bring in new hardware. They don't have to worry about new threat vectors because they're using their existing workflows that they know work. They can be using their existing hardware that they know works. So we are an extremely effective and cost-effective solution to bringing post-quantum capability and post-quantum encryption today.
So would it be fair to say that that getting to post-quantum encryption, instead of rip and replace, what we can enable is orderly tech refresh?
That's exactly what we're saying. And again, you can deploy it anywhere. So if you're in the data center, if you're in cloud, if you're dealing with mobile devices, you can use our solution and use it in any number of different ways to get the best result.
The idea is it fits in standard packages. You don't have to change one line of application code.
Right.
It simply is part of your infrastructure and nothing around it changes. Dave and I have very, very similar professional backgrounds, and we know how cumbersome and brittle security is. And this was designed knowing that most installations have those requirements.
So before we close, let's talk a little bit about the objections. What are we hearing from folks that don't think this is real or don't think that it can become real?
That's a great question. We do hear that. One of the biggest misconceptions people believe is that we are deterministic. We are not. Or that we're a large language model. That's a form of AI. It's a really powerful form of AI, and it's cool, and we all use it. That's not what we have done. That's not what Scott created. He created a neural network that is generative. It generates entropy. And we generate it at scale, at speed, but also, again, the veracity of that data is not in question because we can score it statistically, we can score it looking for patterns, we can do all those things right now. So we don't suffer from many of the misconceptions that people have about what we do. In fact, the entire model runs in about 150 meg for the generation, and in 60K, I believe it is, Scott, 60K for the scoring mechanism. So it's a very, very small footprint versus, say, other forms of AI like LLMs that can be megabytes of data.
So if we think about the AI world, we really have two forms of problems. We have the problems that are like encyclopedias and dictionaries, and you carry on conversations and you look for answers. You see those on Gemini AI commercials on your television. That's what Dave just referred to as large language models. And then we try to ask them more specific questions to kind of direct them. That's one whole form of AI. We're not that. Then there's another form of AI which says, give me a very, very specific problem. Give me a facial recognition when I can't see the face, or give me entropy with a score that's quantifiable and mathematically provable. That's not an LLM. That's a very, very specific type of AI problem. And if you look at the AI world, that's really how it's divided. It's into LLM worlds and utilities. We're in the utility world.
The other thing that I brought up was many people think of that what we have done is deterministic. It's not. AI is non-deterministic by nature. And the other thing that is quite powerful is if you look at QRNGs, if you look at other random number generator sources that NIST approves of, they require the minimum of the seeding of your entropic source to be at least 256 bits. Ours is 4,096. No one, not even a quantum computer, is going to guess or brute force what we can generate when it comes to our encryption keys.
And what's exciting for us, Dave, is we're working on a paper with Cambridge, and we're going to find out that sweet spot of key length versus your entropy score and find out how long it takes to crack and how valuable that is statistically. So not only do we know where we are and we're making it better, we're going to have real mathematics to tell you how far ahead of the curve you actually are.
Exactly. And again, I'm going to come back to the biggest objection: time. How much time, how much effort, how much energy, what's the cost of implementing a solution like Entrokeys? Well, what we're saying is none. You don't have to change your application source. You don't have to change your workflows. You don't have to change your hardware. We work with what you have today. We ensure and make better your encryption technologies today.
Love it. So Scott and David, thanks. A couple of things I'd just like to close us out with. First of all, this is a pressing problem. This is not a problem that's coming tomorrow. It's not a problem that only arrives when quantum computing arrives. It's a problem that's here today because of AI and the patterns that it can recognize that people can't, as well as the threat of harvest now and decrypt later. So what to do? We can all spend tens or hundreds of billions of dollars changing out our hardware and still wind up with a subpar solution, or we can adopt a software-only solution that has the ability to score itself, to know at what level it's performing, and can be implemented without rip and replace. It can be implemented now. It's available today, and it can allow rip and replace to become ordinary tech refresh. At the end of the day, what this comes down to is you don't need to change the hardware. You just need to change the keys.